Hello, my name is Adrian O'Sullivan. I'm doing a PhD with control engineering based on wave energy. I'm currently doing it in UCC, based in the Electrical and Electronic Engineering building. I'm under MARI and getting funded by the SFI. This video is covering the paper I've submitted, and this is hopefully one of many videos that I'll be explaining the paper. And this is the first video where this video and hopefully others were going to be based on the paper wave to wire power maximization from a wave energy converter, where the first part is based on the modeling. So that would be based on the hydrodynamics continuous system, and how I got the small things like the stiffness force, the radiation force, how do I estimate the forces such as Pronys exponential approximation, model reduction, Hankel singular value decomposition. So they're all linked as time signatures down below in the description. The first part is the hydrodynamics continuous system, where the equation is made up of a summation of forces exerted on the wave energy converter, where the entire force of the system is the system's mass by its acceleration, z double dot, and that's equaling to the stiffness force F of h, the radiation force F of r, the excitation force from the waves themselves F of e, and the external force or controllable force FPTO, which can be from a non-ideal or an ideal system. M is the mass of the WEC, and where WEC is an acronym for wave energy converter. F of h is the stiffness force, as I said beforehand, where F of h is minus beta z. Since the system is a point observer, I can say that I'll base a theory off a linear wave theory, hence making this system a linear system. Other systems would have nonlinear factors such as z squared, but in this case it's a linear system, so I can assume it's going to be just z by a gain factor. And this is fairly important for this theory. F of r is the radiation force. About 80% of this video is based on this, how I got it, how I modeled it, how I reduced the model whilst maintaining the main information in the system. And this is the force exerted on the wave energy converter from the waves which were radiated from the wave energy converter's previous movement. The radiation force can be represented by an impulse response which was taken from a WAMET data, where WAMET is a hydrodynamics software. It's found using hydrodynamics software such as WAMET. WAMET produces multiple things such as the non-causal transfer function of the wave height to excitation force, the infinite mass value, and more importantly the impulse response of the radiation kernel, such as this one here, which has units of Newton second per meter, where h of r is the impulse response, which has Newton seconds per meter, and velocities meters per second. So the entire one is newtons, which makes sense. And this method is called the Cummins transformation. With this impulse response WAMET data, the impulse response can be represented as a state space system. It's a standard model where the input into the system is z dot, the WC's velocity, and the output is the radiation force. Using Pronys approximation, a state space system can be made which represents that state space system, where Pronys method includes a summation of exponential values with their corresponding coefficients. So this is just a small example where we have some WAMET data sets, f of 0, f of 1, and all the way down to f of n. And it's up to you how many exponential coefficients you want. That's just a little mistake there. But it's up to you if you want tons of exponential values, so it's C1, C2, up to something like C50. But in this case, I'm just after taking 2. So the more the exponential coefficients, the more accurate the system is going to be to the actual impulse response itself. So in this case, we're just using 2. So you can see here that the exponential value here of 0 is 1, and then you got the exponential of 1 by u of 1 is exponential by u of 1, and then you can see it's the exact same thing underneath except with an n. So that makes sense. Just going on to the next part now. And please leave comments below. I am not shy of answering anybody. From this we can make a polynomial, a general polynomial. This gets much larger the more exponential values you put into it. But in this case we're just using 2, so we got 2 lambda values. And we know from here that if we leave z equal to b1 or b2, p is going to be equal to 0. So it can be said that C1 by P of B1 plus C2 by P of B2 is equal to 0. This makes complete sense. And you can say the exact same thing except adding or multiplying it by another B factor below. And this method can be repeated for many points depending on your data length. So filling in, we get these 2 equations here. And from here, the equations can be broken down even further. And in this form, it's probably the easiest form to see what exactly is happening. So we got C1 plus C2, which is f of 0, C1 by B1 plus C2 by B2, which is f of 1, and C1 by B1 squared plus C2 by B2 squared, which is equal to f of 2. So they're all the data points multiplied by the lambda constants. So from here, with the other equation as well, we can make a matrix equation where it's easy. Let's just call the matrix on the left G and the matrix on the right H. So we can inverse the G matrix and easily find the lambda values. And from the lambda values, we know that they're equal to B1, B2, and B3. And from there, we can, when we solve B1, B2, and B3, you can solve for B or C1 and C2. So it's easy to find the coefficients. So the overall equation for this one would be this one here. And this is probably the best thing about Pronys. It's really easy to put the continuous into the Laplace since it's already in exponential form. And from here, we can put this transfer function format into a state space format really easy. For the best approximation, a higher amount of exponential values is definitely much better to do. However, increasing the exponential order definitely increases the complexity of the system, where if you actually put that order in that state space system with that order into the simulation, it could take ages. So to combat this issue, you increase the system's order to get the best approximation, and then you use the Hankel singular value decomposition method to do a balanced system reduction. So to explain the singular or Hankel singular value decomposition, I'll explain the Lyapunov equation first, where it is used to transform an unbalanced system into a balanced system, which is essential for this method. And these are the two Lyapunov equations here. Here we go. Where P is the controllability grammarian. Here you go. And Q is the observability grammarian. If the system is completely balanced, the controllability and observability grammarians will be equal to each other, but most systems are not equal or not balanced, so they won't be equal to each other anyway. So if the system is balanced, you can say that P and Q are equal to each other. In this case, it's sigma, and the corresponding A, B, and C, if the system is balanced, will be a balanced new system. So it's got A hat, B hat, and C hat. So this is the fundamental theory of the Hankel singular value decomposition. But unfortunately, this method is very tedious to do by hand. So fortunately enough, MATLAB's got some functions that can help you, such as the HSVD and the balance reduction function, where if you insert a system into HSVD, it will plot out the balanced observability or controllability grammarians and their eigenvalues on a graph, and from there you can see what the power distribution of the states are, and from there you can declare what order you want the balance reduction to be, and then you'll get your balanced new system by using the balance reduction function. An example here of the HSVD, let's just take a random state and a random state space system here. Let's say we plot it with the HSVD function, and you'll get something like this, with power of the states on the y-axis and the state numbers on the x. And if the system is stable, you will get blue bars. If you use Pronys, you'll get something like this. You might not get this if you use a random system, but you can see here that the first three states are the dominant states. So from here, and this is something that you want to look out for, if one of the bars is red, it means that that state is unstable. And if this happens, I would highly advise you to go back and have another look at your system identification system, just in case you're not using Pronys or you're using it for a different application, because you just can't reduce it any further. From the HSVD graph, it was shown that roughly 3 states obtain the majority of the power. So by using the balance reduction function, we can declare that we want a balance reduction of the system, and we want a third order system. And you'll get a new system, A hat, B hat, C hat, D hat. And if we test the size of A hat, we'll get a 3 by 3, meaning there's 3 new states instead of 64 or whatever your model was before. And so the model is significantly decreased whilst still maintaining the majority of the system. So it's about 95% of what it was with a much more decreased system. So happy days. With the radiation kernel represented by a satisfactory low or estimation at a low order, The system can be written as a standard state space system, where we include the new states of the radiation kernel into the hydrodynamics continuous system. So this is the original hydrodynamic system in the state space form, including the states of the radiation kernel. And we can see here that the only difference here, besides the x of r at the bottom, is that we have the derivative of z dot is equal to the original hydrodynamic system, but we've also got another term here of cr by z dot, and that's, if you go back to the previous slides, you'll find that that is the radiation force. So thanks for watching, and leave comments. Thanks.